Hello, welcome. In this short video, let us look at the derivations of recursive expressions for the mean, covariance and variance of first order Gauss Markov process. So given the state model, which is a first order Gauss Markov process, S of n is equal to a times S of n minus 1 plus U of n. This is the first order Gauss Markov process where the error term U of n follows a Gaussian distribution with mean 0 and variance equal to sigma square. And the first state, that is S of minus 1, also follows a Gaussian distribution with mean mu s and variance sigma square s. Excuse me, this should be sigma square u. So our goal is to derive recursive expressions for the mean. It is expectation of S of n in terms of expectations of S of n minus 1, and then covariance of S of n comma S of m, that is denoted as Cs of m comma n, and the variance of S of n. Basically, we have to represent all these quantities in terms of the moments from the previous term, that is in terms of S of n minus 1. So let us look at the mean first. Expectation of S of n is equal to expectation of a times S of n minus 1 plus U of n. And since expectation of U of n is assumed to be 0, we can ignore that term. So we are left with a times expectation of S of n minus 1. Therefore, expectation of S of n is equal to a times the expectation of the previous state. This is the first recursive equation. Next, we want to look at the covariance term. By definition, the covariance term, that is Cs of m comma n, is equal to expectation of the product of the following differences, that is S of m minus expectation of S of m and S of n minus expectation of S of n. And this is equal to expectation of, by using the model for S of n, we have a times S of m minus 1 plus U of m, and the expectation of S of m is given by minus a times expectation of S of m minus 1. So this is the first difference. The second one is a times S of n minus 1 plus U of n minus a times expectation of S of n minus 1. This becomes expectation of a times S of m minus 1 minus expectation of S of m minus 1 plus U of m, and then we do the similar manipulation for the second term, that is a times S of n minus 1 minus its expectation plus U of n. So upon expansion, we have expectation of a square multiplied by S of m minus 1 minus its mean, that is S of m minus 1, expectation of S of m minus 1 multiplied by S of n minus 1 minus expectation of S of n minus 1. And then we have expectation of U of m multiplied by U of n. And the rest of the cross terms can be ignored because the error term is assumed to be independent of the actual signal component. That is S of n or S of n. That is U of m is independent of S of m minus 1, and similarly U of n is also independent of S of n minus 1. So this is equal to a square multiplied by expectation of s of m minus 1 minus expectation of s of m minus 1 into s of n minus 1 minus its expectation. This is clearly the covariance for the previous terms. And then we have the variance of the error term, which is sigma square u. Therefore, the covariance at m comma n, it is between two states s of m and s of n, is given by a square multiplied by the covariance from the previous states. We have m minus 1 and n minus 1 plus the variance of the error term, that is sigma square u. So this is the recursive expression for the covariance. Now we can easily derive the expression for the variance term by using m equal to n. We have variance of s of n is equal to a square times variance of s of n minus 1 plus sigma square u. This is true because at m equal to n, the variance of s of n is same as the covariance. Thus we have recursive expressions for the mean, that is this one, and the covariance and the variance. Thanks for watching.